It fills my heart with gratitude immensely, especially towards the Kuwait chapter of ASSP for having considered my humble contributions worthy of your time. And more importantly, to just give in my 2 cents to what Mr. Ritwik has already stated. Process safety is more about being aware of the situations, having the enough know-how to look for the hazards, identify them appropriately, and see them happening so that you can effectively manage them. In my sort of experience over more than a decade and a half in this industry, what I have now come to know and very humble to understand is that process safety is about hazard identification. And to what Mr. Ritwik has actually said in the beginning, very pertinently, is that it is via association, it is via engagement that we learn. And the more we learn, the more we can do this hazard identification. And the more hazards that can be identified, it can be assessed and managed appropriately. And then, inshallah, we can, as safety professionals, as cohorts in the major accident hazard industry, we can ensure what now one of our friends just said, zero LTI forever. Thank you, ASSP, for giving this opportunity. And may I please check, is my presentation now visible to all?
Yes, yes, sir.
Yeah, you are very much.
Oh, yes, thank you. So without further ado, I would just like to take it forward. Here, I have been given this opportunity to talk about experience sharing. And the topic that we will be looking towards here is about to err is just human. A little bit about myself. I am Rahul Patteri. I've got a master's in process safety. I've got a working knowledge in functional safety. Like we said, I've got a decade and a half of working in the major accident hazard industry. My career, I started as a firefighter, slowly moved into the EPC business of onshore and offshore. And by the grace of God and the will of understanding, I was able to work as a consultant for process safety hazard industries into consequence modeling and risk assessments, and also run certain computational fluid dynamics. And now presently, having the good fortune of, how do I say, bringing all this knowledge into operations as working as an operator for an offshore and now presently into an onshore industry. Moving forward, we will be looking through the basics. We will be talking about combustion. We will be talking about energy. We will have a little bit about gas turbine and about the crux of the moment, sharing of experience, the failures and causal factors. Like what Mr. Ritwik was stating, it is through mistakes that we learn. Fail means our first attempt in learning. So what is combustion? Combustion, as we all know, it is fuel which gets mixed with oxygen in the ambient. And as it gets some heat, it produces forms of energy like heat and light. Certain examples of combustion are matchstick for people who like campfires and talking over stories and camping. And of course, our bread and butter, which is cooked. So that particular process is also combustion, wherein fuels of various types gets mixed with oxygen to have a flammable mixture, which when ignited gives us forms of energy. Talking about combustion, we cannot do away with what a fire triangle means. What is a fire triangle? A triangle is having 3 components. So for an effective fire to be generated, what is said is that we need to have, please bear with me so that I can bring in the laser pointer. Yes. So for a fire to happen, we need to have three ingredients. Like we said, for combustion: fuel, oxygen, and heat. So as per the understanding of fire triangle, it means that for extinguishing fire, if one of these legs are removed, we might not have a fire. So like, for example, if we don't have oxygen, it can be called blanketing. If we remove heat, as we all know, it is cooling. And if there's no fuel, it's called starvation. But then there is a caveat, there is a difference of understanding. Let's see via this example. This is a burning pan. For those in the industry and those who have seen in YouTube videos, this is a burning pan. They put in some sort of a flammable mixture, mostly gasoline or diesel. It gets ignited, and then putting onto the fire suit, a person comes up with, let's say, a dry chemical powder and sweeps the fire and extinguishes it. But then, may I now please ask a question? How did we extinguish this fire? Because we still actually have oxygen. There is a lot of heat still present. And of course, fuel is there in plenty. Well, there might be some people who thinks that, yeah, well, dry chemical powder removes the oxygen. Well, it's a very good guess, but actually not. So this particular dilemma or this particular question, like what Mr. Ujjwal Ritvik said, it's by questioning you learn. And there is no, how do you say, stupid question. There could be stupid answers, by the way. So how did this actually extinguish? And this went back to the researchers at the day, to come across with something called as a fire tetrahedron. So from a triangle, we started to learn about something called as a fire tetrahedron. So what is this particular thing called the fire tetrahedron, which actually extinguished the fire? It is in fact called as the chain reaction or a chemical chain reaction. So going back to this example and the question once again, how did we ensure that the fire was extinguished? It actually is because while there is fire or there is combustion, along with fuel, oxygen, and heat, in order to support combustion, there is something called as a chain reaction of H plus and OH minus. For the matter of the conversation, let's call it as chain chemical reaction or chemical chain reaction. The dry chemical powder sort of inhibits this chain reaction, and therefore what happens? The fire is extinguished. Let's move forward. So now, once having understood what combustion is, having understood what the paradigms of combustion had been, for example, the fire triangle and fire tetrahedron, now let's come to energy. What is energy? I mean, any higher secondary student or even a secondary student would say that it is the ability to do work. What are the various kinds of energies that we know? We have potential energy, kinetic energy, chemical energy, mechanical energy, nuclear energy, solar energy, and the list goes on. But then let's see this topic or this word called potential energy. Well, for all the safety cohorts or the safety champions in the group and now listening to us, may I please ask, what is a hazard? Well, we know one of the most known ISO definitions, which states that it is the potential for harm. See, potential and potential. What is the meaning of potential? Potential means that it could cause a harm. So what is potential energy? It has energy which could be used. So that is potential energy. And what is kinetic energy? Kinetic, by the word kinetic, means energy in motion. So when any object or any physical entity moves, there is a kinetic energy. Let's look for pictures as examples. So here we see this boy having a ball and having our definition that we have understood potential. This ball has the potential energy. So it is static. it has a potential energy. The boy drops the ball, so the potential energy now gets converted to kinetic energy. Let's talk about an archer. So here in this example, the archer using his bow has stretched it. So it has the arrow over here has the potential for moving forward. And as it moves forward, as the person removes the strain on the bow, it has kinetic energy. So now, moving on to chemical and mechanical energy. What is chemical energy? Our human body, in fact, is. We eat a lot of these food. Those food via digestion and hormones get converted to give us ATPs or energy, which helps us to move mechanically. Talking about people, let's look at automobiles. And we all know how the fuel, a chemical inside the engine, gives its a thrust for it to accelerate. So that is a few examples of chemical and mechanical energy. Having understood what an energy is, the various types of energy, let's come to something called as the law of conservation of energy. So again, the vocabulary over here, the conservation of energy. So what will it mean? It means that energy can neither be created or destroyed. It is omnipotent, it's perennial, it can only be converted from one form to the other. It cannot be destroyed, and as something cannot be destroyed, it is not created, but it can be converted to various forms, and it is via this conversion that we have been able to make use of our energy for our daily lives. And something that most of us would know about Newton's third law of motion, which is that every action has an equal and opposite reaction. For example, now a rocket to move forward, how does it happen? It is actually moving forward is a reaction to the combustion of gases and the exhaust propulsion downwards. The flight that takes us places also has these engines which work as turbines to take in air through the inlet. There is a combustion here. It gives us drag, which gives us the thrust to move forward. So moving forward is a reaction to the expulsion of gases. And of course, to all our, for most of us who have been married and having kids, we must have seen our kids watching cartoons wherein the cannon fires and then there is a recoil. So the recoil of the cannon is the reaction to the forward motion of the cannonball. So that's the Newton's third law of motion. Let's recap the basis. I'm sure people amongst us must be thinking, why are we doing this basics? But please stay in with me. It is because the thing is going to come. So we looked into combustion. We looked into fire triangle, fire tetrahedron. We saw about energy, the various forms of energy, and we looked into the laws of motion. Now, let's come to what we all have been waiting for, gas turbines. In the industry, gas turbines are called by various names or synonyms. They are called as gas generators, some call as gas turbines, and there are a few who call them as gas engines as well. So, what is a gas turbine? So, as we said, gas turbine is something that converts one form of energy to another. And as we've seen in the basics, the law of conservation of energy is that it cannot be created or destroyed, but to make it advantageous for our daily lives, it can be converted from one form of energy to the other. And gas turbine, in fact, converts chemical energy into mechanical energy. So gas turbine is something that helps us to convert chemical energy to mechanical energy. It is used in the industry quite rapidly for generation of electricity. It is used to run compressors, pumps, or any sort of rotating media. It can also be used to propel exhaust gases for regeneration of reactors, for surge control, for so many such wide range of applications so deemed necessary. Talking about gas turbine, there are a few sections of gas turbine. We've got air intake, we've got a compressor, we've got something called as a combustion zone, we've got expansion, and after every expansion there is always exhaust. So we've got air intake, like any engine, because gas turbine, we said it's also an engine. So in our fire triangle, what did we know? We need to have oxygen or air. So air is taken in. And what does compressor do? Compressor, by the word meaning compression. Compression means to take whatever in one state and compress it. And while you compress it, what happens? Your pressure increases. And for the chemistry cohorts or the chemistry stalwarts in our group, we all know by Boyle's law, when pressure increases, temperature increases. So now talking about our fire triangle, we've got air, we've got a compressor which actually compresses air and thereby increases the temperature. So the compressor gives heat. And then what was needed? It needed fuel to come in. So in this combustion zone, fuel is injected, which we will be seeing later. And it is via the happening of these three together that we get a sustainable combustion, which is then the product of combustion. Those gases expand and send as exhaust. So these are the sections: air intake, which gets compressed, combustion, expansion, and exhaust. The working of the gas turbine, it is just a sort of a pictographic representation of what we just saw. So cold air is taken in, the compressor is started, so we see the cold air gets now pressurized and therefore it is shown to be heated by the color. Fuel gas is mixed. So here what we have as per our fire triangle, we have the oxygen, we have the heat, and we have the fuel. Now, as a spark is generated, it produces a stable flame. And when a flame happens, a flame is a combustion reaction, and it will have its byproducts, which are gases. Those gases which when released from high pressure goes to these turbine blades. These turbine blades, because of the propulsion of gases in a particular angle so defined by the machinists of the turbine, it now provides a rotary motion or a mechanical motion to the shaft. So like we said, a gas turbine here converted a chemical energy to a mechanical energy via means of a shaft. And here, if you put in a generator, you'll have electricity. If you put in compressor, you can compress. You put in pumps, you can pump liquid. And then even if you don't have a shaft, using exhaust gases, you can actually use this energy for heating or any sort of this media. Quickly moving by, the air that comes in has to be uncontaminated. And therefore, you've got filters, and these filters have something that we call as a delta P. It's a differential pressure gauge which looks into, and if there is, how do you say, a reading exceeding the normal, which means that these screens or these filters are trapped. PT is called a pressure transmitter. TT is called a temperature transmitter. And there are more instrumented protection controls. For example, there are pressure and temperature sensors at the compressor. Why? Because just to ensure that there is enough temperature and the pressure is not too high. There is, of course, a fuel gas ratio and mixing sensors at the combustion side to ensure proper combustion. There is something called as a flame stability by means of an optical flame sensor. It looks into how your flame stability is. Your speed and RPM is checked. There is something called as a surge protection. There is blow off valve. There is condition monitoring and all those good things which potentially provide an opportunity we can discuss later. So now gas turbine, how will it look in the field? In the field, it will look something like this. It could look something like this. Pictographically, it could look something like this. And so now, what is the difference over here? If you see, it's all in an enclosure. And these enclosures are actually acoustic enclosure because there's a lot of noise generated as part of this medium, because the RPM, the revolutions per minute, can be as high as 4,000, 5,000 RPM revolutions per minute. And something which rotates, we all know, generates sound, and this can generate massive sound, and therefore there are mostly into acoustic insulations. Now coming into something that happened in one of the facilities, wherein one of these generators where one of these gas turbine generators were used, and these gas turbine generators, the exhaust from these gas turbine generators goes to a heater. This is in an oil and gas installation, and then that particular exhaust gas, having heated up a little bit more, goes to reactor for its purge cycles. So what happened here specifically is that there is something called as a transition piece. A transition piece is just to ensure that the it is something like a vortex cut. So what happens, all these exhaust gases will have various turbulences. And this sort of transition piece makes these turbulent flow to be a laminar flow. So what means is that it sort of disarranges, or it limits the disturbance of flow to have uniform flow to the heater. So here, while this transition piece, or while something was working, the particular operator had a sudden shutdown sequence from the from the gas turbine generator. Why? Because the flame detectors within the enclosure detected hot air. So what means, when a flame detector outside a particular, as we said, there is an enclosure, and when a flame detector detects a hot air, which means that there has been a loss of containment, which means something which was supposed to remain in the turbine went out, which means there's a leak, which is not good. So when this happened, they all went to check what happened. So here in this picture, what you see is this transition piece. So the turbines and all are upstream of this, and downstream is the transition piece. Having closely looked, we saw that there was this particular nipple, and a connection from this nipple had fallen down, and therefore what happened, hot gases were leaking from it, which got detected by the flame detector, because the flame detector also detects IR, infrared radiation. So now, when this happened, the team, including myself, what we saw that there was welding and bracing of this particular nipple. This area, as you see, has been welded, and ideally it is one cast piece, and there should not be welding, because what we all know, welding on a cast piece or a seamless piece means this is the weakest link. So now we went ahead to dig what happened. So this particular nipple that we saw, as per the OEM means an original equipment manufacturer, what he had provided was this nipple, which was snug between these small thin plates. But what had happened is, before an incident what happened when in these plates had deformed a little, because of which there was too much of stress at these small lugs, and the lugs gave off. When these lugs gave off, there was a high demand from the operator side. So what did they do? They went ahead and they welded this piece, because as this had broken down, they had to weld in. Why? Because only then this nipple will be in contact. But then what happened? Maybe because of poor welding or heat treatment process, that weld also gave off. And when this weld gave off, also did the threading fail. So then what happened? We then had a makeshift arrangement, had put in metal plates and then welded it back again. So something which was supposed to look like this on site was like this. So the investigation team came and said, oh yes, this is a human error. This is a human error, poor workmanship, and that was what led to all the particular things. So here, as we see, as we were saying, there was also some stresses on this particular nipple. Why? Because it did not have sufficient supports given. And ideally, we also saw that in order to keep these transition piece in place, there was no place to actually rotate it. So mechanics used to use these lugs as their hold points to maybe rotate it and fit it for the belt to be placed. So now coming in to err is human. How many times to err is human actually means human error? Let me please raise it to all of us here, irrespective of whichever industry where minor incidents have happened. It always boils down to human error being called as the root cause. I, for one, with my little know-how, don't really think so. Why? Because a human error is a contributing factor, but can never be a root cause. For example, here, a few of the root causes are the operations or the machinists went to do heat treatment on a piece without consulting with the original equipment manufacturer. There was no management of change in place. There was no piping support and stress analysis conducted. If there was a transient analysis performed, we would have known about the king points. There was a design limitation and an operational constraint for this particular person to go and fit this transition piece in place. So like we were saying, a human error can be a contributing factor, but it's not ideally a root cause. Mr. Ujjwal Ritvik actually stated this person's name, calling him to be his mentor. And he stated that people who say that accidents are due to human error is something saying that falls are due to gravity. And it is told by somebody called as Dr. Trevor Kletz, who is known to be the father of process safety. Here we come to our end of this presentation. Credits go to YouTube videos. It goes to references from the internet. I follow something called as a golden circle, the why, the what, and something called as the how. The why is very similar to what ASSP, Mr. Ujjwal Ritvik, said, that it is to democratize learning, make learning interesting and illustrative. What will we achieve? By learning, we achieve associations and engagement. And what happens? We will be able to identify hazards better. And how do I do this? I have a YouTube channel called as Loss Prevention Maverick. My peers have said that even if you check Rahul Patteri on YouTube, you will come to know of this channel. In my channel, there is always a portion for gratitude. And here I would like to pay my respects to my father and mother who are still with me. If not for them, I would never have had an opportunity to pursue my career. Specifically, when I was starting, safety or process safety was not something very lucrative, but they never stopped me from pursuing my career. And thank God that now I have an opportunity to save lives, and like what Kishore said in his presentation, have an opportunity to ensure that incidents do not happen that kill people. Thank you very much to all for listening to me. Thank you.